In this video, we're going to take a look at trig identities. And first up, we're going to derive what are known as Pythagorean identities. So Pythagorean identities are some of the most important identities in a course using trigonometry. And they're based on the Pythagorean theorem, hence why they're called Pythagorean identities. So our first Pythagorean identity is the most common one. It's that the cosine of an angle, when we square that ratio, and then add that to the sine of the angle, that ratio squared, we're always going to get 1. Or to put it more familiarly, cosine squared of an angle plus sine squared of that angle is always going to equal 1. So here we have a right triangle with x, y, and r. And we know that x squared plus y squared is r squared by Pythagorean theorem. Now, depending on what you divide both sides of the equation by, you'll end up with one of your 3 Pythagorean identities. Our first one here is we're going to divide everything on both sides by r squared. So we get x squared over r squared plus y squared over r squared equals r squared over r squared. Now, x squared over r squared is x over r, that fraction squared. Y squared over r squared is y over r, that fraction squared. And r squared over r squared is 1. Now, when we talked about trig functions of any angle, cosine is x over r, sine is y over r. So this becomes cosine of the angle squared plus sine of the angle squared equals 1. And we typically write the exponent between the trig function and the angle. So we would typically write it as cosine squared theta plus sine squared theta equals 1, as opposed to cosine of theta, that results squared. Example 2, we have 1 plus tangent squared equals secant squared. So we're going to start again with x squared plus y squared is r squared. This time we're going to divide everything on both sides by x squared. So dividing every single term by x squared, we get 1 plus y squared over x squared is y over x, that fraction squared, equals r squared over x squared is r over x, that fraction squared. Now y over x is tangent of theta, r over x is secant of theta. So this becomes 1 plus tangent of theta, that expression squared, equals secant of theta, that expression squared, which then we can write our exponents between the trig function and the angle, giving us 1 plus tangent squared equals secant squared. Our third Pythagorean identity is a result of taking our Pythagorean theorem and this time dividing by y squared. So if we divide everything by y squared, we're going to get x squared over y squared is x over y, that fraction squared. Y squared over y squared is 1, and r squared over y squared is r over y, that fraction squared. So x over y is cotangent, r over y is cosecant, so we have cotangent squared plus 1 equals cosecant squared. We have some alternate forms of our Pythagorean identities. We'll look at the most popular one here, cosine squared plus sine squared equals 1. If we subtract sine squared from both sides, we get cosine squared is 1 minus sine squared, which then we can factor 1 minus sine squared as a difference of squares. So that cosine squared is 1 minus sine times 1 plus sine, because 1 minus sine squared factors as a difference of squares. In addition, we could have subtracted cosine squared from both sides, and we'd have sine squared equals 1 minus cosine squared, and 1 minus cosine squared is also a difference of squares. So that factors as 1 plus cosine times 1 minus cosine. Our other 2 Pythagorean identities also have that similar characteristic. So we have 1 plus tangent squared equals secant squared. If we subtract 1 from both sides, we get tangent squared is secant squared minus 1. That factors as secant plus 1 times secant minus 1. So tangent squared also equals secant of theta plus 1 times the secant of theta minus 1. If we instead subtract tangent squared from both sides, we get secant squared theta minus tangent squared theta equals 1. And secant squared minus tangent squared is secant plus tangent times secant minus tangent. So we get another difference of squares factorization here. Finally, our third Pythagorean identity, 1 plus cotangent squared equals cosecant squared. If we subtract cotangent squared from both sides, we get cosecant squared minus cotangent squared equals 1. The left side factors as a difference of squares. And if we subtract 1 from both sides in our original identity, we get cotangent squared is cosecant squared minus 1, which the left-hand side, again, factors as a difference of squares. Our next identities we're going to look at are what are known as the quotient identities, which allow you to express tangent and cotangent in terms of sine and cosine. So the tangent of anything of any angle is the sine of that angle divided by the cosine of that angle. And the cotangent of any angle is the cosine of that angle divided by the sine of that angle. So use the triangle to verify that tangent is sine over cosine. So let's start with sine over cosine. And in terms of our triangle here, that's y over r for sine. And in terms of cosine is x over r. So we have sine over cosine is y over r divided by x over r. Now we have this complex fraction, so if we multiply both numerator and denominator by r, it'll clear out our fractions, tiny fractions, and we have y over x. And y over x, going back to trig functions of any angle, is your tangent. Next up, we have sum and difference identities. So here I have a list. You might want to pause the video and write these down, or you can refer to the handout that I made available in class online. But here we have our angle sum and difference identities for sine, cosine, and tangent. And at the bottom here, it notes that, again, the tangent of a plus b is the sine of a plus b over the cosine of a plus b. And then the tangent of a minus b is the sine of a minus b over the cosine of a minus b. Again, reinforcing that idea that tangent of anything is the sine of that angle over the cosine of that angle. So example 5, we're going to verify the cosine of pi over 2 minus theta is sine of theta. In other words, when we look at a right triangle, the cosine of one of the acute angles is equal to the sine of the other acute angles, angle. So if we expand out cosine pi over 2 minus theta, we take the cosine of the first angle times the cosine of the second angle, so cosine of pi over 2 times the cosine of theta, and then add to that the sine of the first angle times the sine of the second angle, so the sine of pi over 2 times the sine of theta. Now cosine of pi over 2 is 0, and sine of pi over 2 is 1. So what the right side simplifies to is 0 times cosine of theta plus 1 times the sine of theta, which just gives us sine of theta. So when we, again, verify anything in math, we're showing that the left and right sides are actually equal. Example 6, verify that cosine of negative theta equals cosine of theta. So we can think of negative theta as 0 minus theta, and this will become the cosine of the first times the cosine of the second, so the cosine of 0 times the cosine of theta, plus the sine of the first times the sine of the second, or the sine of 0 times the sine of theta. Now cosine of 0 is 1, and sine of 0 is 0, so we have 1 times cosine plus 0 times sine, and that's just going to simplify. 1 times cosine is cosine, and this goes away because it's multiplied by 0. Our double angle identities are nothing more than our angle sum identities in which the two angles, A and B, are the same. They're equal. So for instance, the sine of 2a is the sine of a plus a, because when we add something to itself, we double it. Well, according to our sine angle sum, it's the sine of the first times the cosine of the second, plus the sine of the second times the cosine of the first. Just so happens to be the same angle measure. So we have sine a cosine a plus another sine a cosine a. Again, when you add something to itself, you're doubling it. So sine a cosine a, when we add it to itself, gives us 2 sine a cosine a. Our double angle identities for sine, cosine, and tangent are given here. So cosine of 2a is cosine squared a minus sine squared a. And tangent of 2a is 2 times the tangent of a over 1 minus tangent squared a. Now, cosine of 2a has alternate forms. The first alternate form is if we use the fact that in cosine squared minus sine squared, we talked about Pythagorean identities earlier, and we said cosine squared is 1 minus sine squared. So if we substitute a 1 minus sine squared in for this cosine squared, we have 1 minus sine squared of a, and then bring down this other minus sine squared of a, and then this gives us 1 minus 2 times sine squared of a. So this is one other form for our double angle cosine. Our other form is looking at the sine squared of a as 1 minus cosine squared. So substituting a 1 minus cosine squared of a in for this sine squared a, we get cosine squared a minus the expression 1 minus cosine squared a. Now distributing our negative through, we get minus 1 and plus cosine squared, and then cosine squared plus cosine squared is 2 cosine squared. So another alternate form for cosine of 2 times a, or our double angle cosine identity, is 2 times the cosine of squared of angle A minus 1. From those double angle cosine alternate forms, we have what are known as power reducing identities. So our power reducing identities or power reduction identities can be derived from our alternate equations for the cosine of 2a. So for instance, with cosine of 2a equals 2 cosine squared a minus 1, if we add 1 to both sides and divide by 2, we're going to get cosine squared a is 1 plus cosine of 2a all over 2. For our other one, we have cosine of 2a equals 1 minus 2 times the sine squared of a. This one should say solving for sine squared a, not cosine squared a, so I apologize for that. But subtracting 1 from both sides and dividing by this negative 2, we'll get our sine squared a by itself. And sine squared a is 1 minus the cosine of 2a all over 2. For those of you going on to calculus in the future, whether it be Calc BC or Calc 2 in college, you'll see these identities when integrating trig functions with powers of 2. So, all right, so that about does it for this video. Thanks for watching. I'll